On July 1, 2025, astronomers spotted 3I/Atlas, an interstellar comet moving at nearly 124,000 miles per hour, hurtling toward Mars. Just as it passed our planetary neighbor, NASA's data stream slipped into silence, leaving researchers empty-handed during the moment that mattered most. Why did the world's best eyes suddenly go blind? And what is so unusual about this object that experts now argue it may be engineered, not natural? The case for 3I/Atlas becoming more terrifying day by day starts with the blackout, and only gets stranger from here. The official discovery of 3I/Atlas entered the astronomical record on July 1, 2025. Its formal designation, 3I/Atlas, places it as only the third interstellar object ever confirmed to cross into our solar system. The detection came not from a single observatory, but through a network of ground-based telescopes working in concert. Automated survey logs from that night show a faint, fast-moving point of light streaking against the background stars, clocked at speeds near 124,000 miles per hour. Within hours, the Minor Planet Center issued a circular flagging the object's hyperbolic path and unbound velocity. Veteran astronomers quickly realized this was no ordinary comet. The inbound trajectory pointed from beyond the solar system, cutting through the planetary plane rather than rising steeply above or below it. Early images, released in the days following discovery, fueled both excitement and debate. NASA's Perseverance rover on Mars managed to capture a streak suspected to be 3I/Atlas, though later analysis clarified that its elongated appearance was partly an artifact of the camera's long exposure. The true shape remained a matter of speculation. As data trickled in from amateur and professional telescopes around the world, researchers began to anticipate a flood of sharper images and detailed spectra, especially as the object closed in on Mars. The expectation was clear. With so many assets trained on the flyby, the coming weeks would bring an unprecedented look at an interstellar visitor. Instead, the astronomical community would soon find itself confronting a sudden and unexplained silence, just as 3I/Atlas reached its most critical vantage point. When 3I/Atlas swept by Mars in early October 2025, the world's astronomers waited for the kind of close-up images and spectral data only NASA's Mars orbiters could deliver. Instead, official websites displayed error messages and broken links. NASA's high-rise gallery, usually updated within hours of new observations, offered nothing but a banner about delayed uploads due to the ongoing US government shutdown. The Perseverance rover's raw image feeds went dark for the first time in months. At the exact moment the comet reached its closest approach, October 3rd and 4th, no new public data appeared from any American Mars asset. Researchers hunting for fresh files on the planetary data system found only routine maintenance notices and a conspicuous lack of 3I/Atlas entries. The timing was impossible to ignore. The shutdown had begun just hours before the flyby, halting all non-essential operations and sending most mission staff home. Under these conditions, only the most critical, safety-related data made it through the pipeline. Requests for special targeting or uploads, such as those needed for opportunistic imaging of 3I/Atlas, simply never happened. Internal logs later confirmed that Mars Reconnaissance Orbiter was not retasked for deep space imaging during the window. Its resources were locked to surface monitoring and health checks. While NASA's data feed stalled, the European Space Agency pressed ahead. ESA's Mars Express and Trace Gas Orbiter continued their planned observations, issuing operational bulletins and releasing summary images within days. Their public archives remained online, with raw files and instrument logs time-stamped throughout the blackout. The contrast was stark. European datasets, though lower in resolution, were promptly available, while the higher fidelity US perspective was missing entirely. For planetary scientists, the absence of NASA's view left a glaring hole in the record, one that would soon fuel debate about whether this was simply bad luck or something more deliberate. Even with the world's best telescopes and orbiters trained on 3I/Atlas, the images that reached scientists were anything but definitive. Early frames showed a faint streak, but the so-called elongated appearance was quickly traced to the quirks of the cameras themselves. Most spacecraft and ground-based observatories rely on long exposures to gather enough light from such a distant, dim target. During these exposures, the comet's rapid movement, over 124,000 miles per hour, smears its profile across the detector. What looks like a cigar-shaped body is often just the trail left behind as photons accumulate, not a crisp outline of the object's true form. Attempts to sharpen these images ran into hard limits. The nucleus of 3I/Atlas remained unresolved, even in the highest resolution datasets from ESA's Mars Express and Trace Gas Orbiter. Instead of a clear core, the images captured only a diffuse envelope, a haze that defied easy interpretation. Signal-to-noise ratios hovered at the edge of usability, with background stars and cosmic rays competing for attention in every frame. Exposure artifacts crept in, sometimes mimicking features that didn't exist. The result was a dataset rich in ambiguity, a patchwork of streaks and smudges where every apparent detail demanded a second look. This technical reality forced astronomers to rethink their approach. Where imaging fell short, they turned to other diagnostics, spectra, which break down the light into its chemical fingerprints, and polarimetry, which measures how particles scatter sunlight. Integration time, the need to collect enough light over seconds or even minutes, became a double-edged sword, revealing faint features but blurring fast-moving ones into uncertainty. The boundaries of what could be claimed from the imagery became clear. With the nucleus itself still hidden, the case for 3I/Atlas would have to rest on evidence beyond the reach of any single snapshot. 3. I/Atlas has drawn quiet fascination among orbital dynamicists for a reason that's hard to overstate. Unlike Oumuamua and Borisov, whose steep, high-inclination paths slice through the solar system at sharp angles, Atlas moves almost as if it belongs here, skimming the ecliptic plane, never veering more than 5 degrees from the flat, invisible track where the planets circle the Sun. For an object arriving from interstellar space, this is not what theory predicts. Most models expect such wanderers to appear from any direction, plunging through the solar system on unpredictable courses. Instead, Atlas glides along the planetary plane, threading a sequence that brings it near Mars, then Earth, and finally Jupiter. No other interstellar object has followed such a choreography. The odds of this happening by chance are difficult to express. Both Oumuamua and Borisov arrived on steep, almost perpendicular trajectories, matching expectations for random interstellar arrivals. The ecliptic, after all, is a thin slice, just a few degrees wide, amid the vastness of space. For a visitor from the void to enter along this narrow band and then pass close to several major planets is a statistical outlier. Avi Loeb, known for challenging conventional wisdom, has described the combination of ecliptic alignment and multi-planet flybys as having odds of less than 1 in a million. No peer-reviewed paper has yet pinned down a precise probability, but the rarity is not in dispute. Astronomers have never before watched an interstellar object weave through the solar system in a way that almost seems to maximize planetary encounters. Orbital simulations reinforce how unusual this is. Most interstellar objects should zip through quickly, rarely coming near any planet. Yet Atlas is projected to pass close to Mars in October 2025, approach Earth in December, and encounter Jupiter the following March. Each alignment is remarkable. Together, they form a pattern that stands apart from anything previously observed. This geometric anomaly has sparked debate. Some caution that 3 interstellar discoveries are too few for sweeping claims. Others, including Loeb, argue the odds are so remote that natural dynamics alone may not suffice. Attention now turns from the path Atlas takes to the physical mysteries it may reveal. Mass estimates for 3I/Atlas have forced astronomers into uncomfortable territory. Calculations based on its brightness, outgassing rates, and trajectory suggest a bulk mass near 33 billion metric tons, orders of magnitude heavier than either Oumuamua or Borisov. Even as jets of gas stream from its surface, the object's course shows barely any measurable deviation. For a comet, this level of inertia is almost unheard of. Most bodies this active shed enough mass to nudge their orbits, but 3I/Atlas moves as if nothing can budge it. That resilience, paired with its sheer scale, hints at a structure far denser or more cohesive than the loose, icy rubble piles typical of solar system comets. This raises a deeper puzzle, sometimes called the missing pebbles problem. If nature is capable of forging interstellar objects this massive, logic suggests there should be a whole spectrum of smaller fragments, thousands of pebbles, boulders, and mini-comets traveling similar paths. Yet after decades of sky surveys, no such population has turned up. The absence of these smaller kin stands out. Selection effects and detection limits can explain some of the gap, but not all. The cosmos seems to have delivered a giant, skipping the expected swarm of lesser bodies. The chemistry of 3IAtlas only deepens the mystery. Spectra from Keck and the Very Large Telescope reveal strong cyanide and carbon monoxide signatures, matching what's seen in classic comets. But the dust itself tells a different story. Silicate-rich grains dominate the spectral profile, pointing to a warm, rocky origin, more like a planetary crust than a frozen relic from the outer reaches of space. Even more unusual, atomic nickel is present in abundance, while iron is nearly absent. This flips the expected ratio found in meteorites and comets from our own solar system. Some teams have tentatively flagged nickel-carbonyl compounds, though the evidence remains debated. Laboratory experiments show these molecules can form under extreme conditions, but the yields are small and the process is rarely seen in nature. Physical resilience was put to the test on September 25, 2025, when a powerful coronal mass ejection from the Sun swept across the object. Most comets fragment or shed large portions of their envelope under such stress. Atlas, instead, responded with a brief, controlled expansion of its coma, then quickly stabilized. No fragments, no breakups, just a measured adjustment, as if the object could dampen or redirect the solar blast. This ability to withstand and adapt to a major solar event has no clear precedent among known comets. Each anomaly, on its own, might be explained away. Together, they build a case for something far stranger than a chance visitor from the void. Polarimetry teams have watched 3I/Atlas with mounting curiosity, noting that its scattered sunlight appears to behave in ways rarely seen in comets. Preliminary reports from ground-based observatories, including VLT and SALT, describe the object's coma as exhibiting strong negative polarization, meaning the light waves scatter at angles and intensities opposite to what's typical for icy bodies. While official numbers and peer-reviewed measurements remain pending, this pattern has drawn attention because it often signals unusual dust shapes or even engineered surfaces. In laboratory analogs, only exotic particle types, spiky aggregates, hollow shells, or metallic flakes produce this effect at the scale observed. Yet, the data from 3I/Atlas seem to go further, hinting at a degree of negative polarization that pushes beyond known cometary behavior. The orbital path itself adds another layer of intrigue. Dynamicists running trajectory models find that 3I/Atlas's course hugs the ecliptic plane with uncanny precision, rarely deviating more than 5 degrees from the imaginary, flat sheet where all major planets orbit. For an object arriving from interstellar space, this is not just rare, it's an almost without precedent. The two previous interstellar visitors, Oumuamua and Borisov, cut steep, high-inclination paths, making only brief, distant passes by the inner planets. Atlas, by contrast, threads a corridor that brings it successively near Mars, Earth, and Jupiter. This choreography stands out, not only for its alignment, but for the way it seems to maximize planetary encounters. Statistical models are still catching up, but among researchers, there's broad agreement that such a path is vanishingly uncommon, if not unique, among known interstellar objects. Shape modeling remains a challenge, with no direct images resolving the nucleus. Still, indirect evidence builds a consistent profile. Photometric analyses and the persistence of a narrow, non-diffuse signal over multiple exposures support the idea of an elongated body, possibly several kilometers long, with a length-to-width ratio far exceeding that of typical self-gravitating comets. In theory, such a form is not only rare in nature, but also highly efficient for minimizing drag and radiation exposure during high-velocity travel across interstellar distances. The elongated profile, combined with the object's stability and resistance to solar events, has fueled speculation about its origins, whether natural or otherwise. Taken together, these optical and orbital anomalies form a mosaic that's hard to dismiss. The combination of negative polarization, ecliptic-hugging precision, and an elongated, possibly engineered shape doesn't fit neatly into any known category. Each feature alone might be explained away, but as the list grows, the case for a simple, natural comet becomes harder to defend. The debate now turns to competing hypotheses, as the astronomical community weighs the evidence and confronts the limits of its own models. Three explanations now compete to account for what 3I/Atlas actually is, each with its own set of strengths and challenges. The first, sometimes called the Trojan-horse probe hypothesis, proposes that Atlas is a mostly natural object, but with subtle deviations, an ideal disguise for a long-duration interstellar scout. Advocates point to the mathematically precise trajectory, the ecliptic skimming path, and the object's resilience to solar events as possible hints of intentional design. Critics, however, note the lack of obvious technological signatures and argue that extraordinary claims require extraordinary evidence. A second idea, advanced by planetary dynamicist Dr. Suzanne F., frames Atlas as a so-called planetary seed. In this view, objects of such mass and composition could be ejected from young planetary systems, traveling through interstellar space until captured by another star. If drawn into the right orbit, such a body might even help jumpstart planet formation. While this model accounts for the object's scale and some aspects of its chemistry, it remains largely theoretical. No direct evidence yet links Atlas to this process, and the mechanism for such ejection is still debated. The third, most conservative explanation treats Atlas as an extreme but natural comet. This model tries to fit all observed anomalies, mass, chemistry, trajectory, within the known range of cometary behavior. Yet, as the list of inconsistencies grows, defenders of this view find themselves relying on increasingly unlikely coincidences. Each hypothesis offers a lens, but none yet provides a complete answer. Every hour that 3I/Atlas remains intact, it carries more kinetic energy than any human-made object ever launched. Even at a distance, astronomers track its path for signs of sudden change, fragmentation, outgassing, or a shift in trajectory. Comets have been known to break apart without warning, and any significant event could redirect debris or alter the object's course, with consequences impossible to predict in real time. The challenge is compounded by the sheer mass involved. A single fragment could rival the size of a mountain, and at interstellar speeds, even a glancing blow would release energy on a scale that dwarfs any terrestrial disaster. Monitoring efforts now focus on the final opportunities for close observation. The European Space Agency's JUICE mission is scheduled to observe 3I/Atlas in November 2025, using its suite of cameras and spectrometers as the probe cruises through the outer solar system. The geometry offers a rare vantage, but the data will not reach Earth until early 2026, delayed by the probe's position on the far side of the Sun. For planetary scientists, this is more than a scientific curiosity. It is a last window to capture critical information before the object fades beyond reach. The sense of urgency is real. Once 3I/Atlas leaves the inner solar system, the chance to answer its mysteries may be lost for generations.